Oh, it's a great pleasure for me to introduce the speaker of today, Professor Peter Clarkson, who is the Emeritus Professor at the University of Kent and the recipient of the Senior Anne Bennett Prize of the London Mathematical Society. He is universally known as one of the greatest experts in the Painleve equations, and as such, he wrote the Painleve chapter of the Digital Library of the Mathematical Function project. So he will speak today about rational solution of Painleve equations.
Thank you, David. So I'd like to thank the organizers for this opportunity to talk in this program, give the seminar on this focus week on Painleve equations. So the outline of the talk, I'm going to give a brief introduction, and I'm going to concentrate on three equations. The second Painleve equation. I shall also look at the hierarchy of the second Painleve equation, the fourth Painleve equation, and then an associated systems, this system of three equations, which Nalini mentioned last week, which is equivalent to Painleve 4, and a system of 5 equations. If I get time, this is the next one in the hierarchy. Paul is joining on, who happened to be at the Newton Institute Program on Complex Analysis a couple of years ago. I gave a variant of this talk at that stage, but there are some new things in this talk from that. So, as we know, the 6 Painleve equations are these 6 nonlinear ordinary differential equations whose solutions are free from movable critical points. And in the notation I'm using, the alpha, beta, gamma, and delta are the arbitrary constants. Now, for the general solutions, we know they're transcendental for all values with parameters. But for special values with parameters for Painleve 2 through 6, we know that there are rational solutions that don't depend on any arbitrary constants as such. And it's those that I'm going to look at today. Particularly, I want to look at some of the properties of the roots and the poles of these equations, because they have some remarkable patterns in the complex plane. Now, related to the 6 Painleve equations are the 6 Painleve sigma equations. These are second order, second degree differential equations. Now, whilst I'm not going to explicitly use them in today's talk, they can be useful in the fact that some of the special polynomials that I'm going to express the rational solutions in terms of, they do satisfy these sigma equations. And it's often actually the sigma equations that arise in the applications more than the Painleve equations in many respects. For example, in random matrices and orthogonal polynomials, these equations regularly arise. So rational solutions of Painleve equations typically have a form that they are linear in Z, and then the logarithmic derivative of the ratio of 2 polynomials, which have no common roots. And these have various names depending on when they're being derived. The first one I'm going to look at, the so-called Jablonski-Voronov polynomials. For Painleve 3, they're known as the Umimura polynomials, and they involve a parameter mu. For Painleve 4, there are 2 sets of polynomials, which we're going to see the generalized Hermite and the generalized Okamoto, and these depend upon 2 integers, m and n. And for Painleve 6, it's the Umimura polynomials, sorry, for Painleve 5, the Umimura polynomials, which depend on 2 integers and a parameter. Painleve 6 does have some rational solutions, but they're in a slightly different category. And so they haven't been as well studied in many respects. Painleve 6 is a different kind of equation, I feel, and it has a lot of algebraic solutions that are very interesting. So the applications of rational solutions of Painleve equations, they've arisen in a variety of different contexts. For example, the Wronski-Laguerre polynomials have arisen in the transition behavior of the semi-classical Sine-Gordon equation, in boundary value problems, and moving boundary value problems, and various symmetry reductions that arise in physics. The Nomura polynomials, and associated with Painleve 3 and Painleve 5, arise as multivariate vortex solution of the complex Sine-Gordon and in wireless communication system. The generalized Hermite polynomials arise in random matrix theory, description of vortex dynamics, supersymmetric quantum mechanics, and as recurrence relation, coefficients of recurrence relations in semi-class orthogonal polynomials. The generalized Okamoto arise in supersymmetric quantum mechanics and can generate some solutions of the defocus in nonlinear Schrodinger equation. And the special polynomials associated with rational solutions are really examples of what are known as exceptional orthogonal polynomials, which are currently under much study. Okay, so let's look at Painleve 2. Now, these have been known for a long time. It's been known since the work of Gambier in the early 20th century that Painleve 2 has a rational solution which is unique, provided the parameter alpha is an integer, positive or negative. It has no arbitrary constants, and it has the form as a polynomial of degree n times n minus 1 divided by a polynomial of degree half n plus 1. And you can iterate the Backlund transform, or use the Backlund transformation to iterate to get the solution from n to n plus 1. And you can use the seed solution of 0, that when n is 0, you get 0. Now, what Jablonski and Laguerre did was they showed that you could express them in terms of polynomials defined by this recursion relation here, with Q0 is 1 and Q1 is Z. Now, what's the remarkable thing about this recursion relation is that at each stage to generate Qn plus 1, you're dividing by Qn minus 1. So you can expect to get a rational solution, but the fact that you actually get a polynomial is just one of the miracles happening in Painleve. And then the rational solution is given by the logarithmic derivative of the ratio of Qn minus 1 over Qn. And that's what the solution is. Now, the polynomials that you get out from this recurrence relation, they have degree n times n plus 1 over 2. So a triangular number, and they go up in powers of 3. It's quite easy to calculate them like this. In fact, that's how originally, when I started looking at them, we were actually calculating them by just actually running them through this recurrence relation to actually generate. And then in 2003, I started plotting them and found this remarkable structure, that they have this triangular structure of where the roots lie. They lie in this triangular region. Now, if you look carefully at it, and you actually look at the numerical values, you see that it's not strictly a triangle. As far as it's not straight edges, there are curved edges. And the question really is, what is the region in which it's coming in? So let me say a little bit more about generating them. We can define a polynomial Pj through this exponential here. You can think about this as a generalization of the Hermite weight of the Hermite polynomial. The Hermite polynomial would have a lambda squared here. And then the Jablonski-Volga polynomials are given by the Wronskian of the odd ones derived here. So you purely take the odd ones. Now we know what this constant c is, but actually the constant c is completely irrelevant because I'm going to take a logarithmic derivative. So I don't actually need to see what that constant actually is. And this is a neater way of actually trying to derive the solution, the polynomial, because you don't have to get the 20th one, you don't have to work out the first 19. You can certainly work out them all directly. Now, because you have a cube here, then the polynomials satisfy a third order equation, a third order difference equation, and they also satisfy a third order differential equation, which you can actually solve in terms of 1f2 hypergeometric function. That's a 1f2, not a 2f1. It's the third order equation. Sorry, wrong way. Okay, now these are actually not orthogonal polynomials, but they're actually multiple orthogonal polynomials, and they're closely related to multiple orthogonal polynomials associated with modified Bessel functions introduced by Van Asch and Jakubowicz. And in fact, there's a recent theorem due to Van Asch and Laguerre and Van Asch that actually expresses these polynomials in terms of the multiple orthogonal polynomials, where we have the kernel is a modified Bessel function. And you can actually then generate what these actually are and know precisely what you have. Now, the fact that a Bessel function arises is not too much of a surprise, because the Bessel function of parameter a third, which is related to ARA functions, and the ARA function is related to other solutions of Painleve 2. And if you look at the roots of these polynomials, I've put for P25, P26, and P27, you see that they lie on 3 rays in the complex plane. So these are polynomials that don't have all their roots on the real line. In fact, they have them on 3 rays. Of course, the rays that you associate with the ARA function. Now, if we define this sigma n to be a minus an 8z squared times logarithmic derivative of one of the Jablonski-Volga polynomials, then it does satisfy the second order second degree differential equation, which is this Painleve sigma equation of order 2 and parameter n plus a half. Now, from this, you can actually show that Qn satisfies a 4th order ordinary differential equation that's bilinear as well. And that, I think, can be useful to prove certain properties of the Qn. In fact, all of the special polynomials I'm going to mention today do actually satisfy a 4th order bilinear equation. And they also satisfy these bilinear differential difference equations as well. So we have quite a lot of equations which the polynomials actually satisfy. Now, I mentioned about the roots tending to a triangle. Well, there's been some studies done a few years ago by Buckingham and Miller and Bertola and Bothner, looking at the limit as n goes to infinity. And now you have to scale the roots by n to the 2/3 times z. And then they lie in this triangular region defined here, where A is a solution of this cubic. And these are taken from the paper by Bertola and Bothner, where they're going into a rectangle. Now, what I've recently done is I've looked at these, but I've started to plot a few of them simultaneously on the same graph. So I've here got 3 of them. And you can actually see from here that not only do they fit all within the same, these are scaled ones within the same region, but they then sort of have a almost self-similar pattern within the region as well. These are going up, I'm adding 5, so these are multiples of 5, and you see one, and you see 5 triangles at the edge there, and these are going up in 4s, and you can see basically the fourfold symmetry in the 4 triangles in the row there as well. I have no idea why that's true. It's just a curiosity of playing around with trying to show that they all went into the same region, and I happened to just put different multiples together, and this is what I found. You see that certain self-similar pattern there. So let's look at more detail about this region. What they said was the vertices are given by zk, which is these 3 roots, which are the zeros of this discriminant of this cubic here, which they got. I'm going to say a little bit more about how you can get these vertices from a different point of view shortly. So the curves meet with an internal angle of 2 pi by 5, and 2 pi by 5 is suggesting a limit to Painleve 1, because we know that Painleve 1 has this 5-fold symmetry. So now let's consider Painleve 2 with alpha equal to n. And I want to look for some kind of equilibrium for large n. So I'm wanting to look for, so I'm going to assume that W is going to be eta n to the 3rd, Z is xi n to the 2/3 for eta and xi constants. And then we get a balance here so that we see that 2 eta cubed to xi eta plus 1 is 0. And then if we look at for transformation of the equation around this equilibrium point, and I'm going to assume that R and S, well, R has got to be less than 1/3, S is less than 2/3, then you can show that R has to be minus 1/15 and S is minus 2/15 by just using a maximum balance argument. And then what you get is you get this equation here. Now, we're looking to limit as n goes to infinity, and so we're going to have to assume that 6 eta squared plus xi is 0 for this to happen. And then if we set a to be minus eta to the 5th and xi to be minus eta to the 2/3 of b, then in the limit you get Painleve 1. And then, of course, I've already shown that eta and xi are related by this, and they're related here. 6 eta squared plus xi has to be 0. And if you solve that, you find exactly what the vertices of this rectangle, this triangle I had before are. So you just look, you're finding this coming from the limit as you would expect. Now, the other aspect about this is if you look for this equilibrium point, and then if you, this is a cubic equation in eta, and if you look for the discriminant, so the discriminant is 0 whenever the equation has a polynomial has a multiple root, and that happens when the zeros of this are given by exactly the same thing I just had. So you're getting this explanation as to where these roots are coming from, as to why you're getting the points of where the points of that rectangle actually are. Now, Buckner and Miller actually showed that as the limit then goes to infinity, the rational solution trends to the well-known tree truncated solution of Painleve 1. So this is this solution that has this very specific form here. It's a monotone increasing function. It looks like the square root of minus the square root of minus x has x goes to minus infinity and has a blow up. And it's well known by the fact that for the generic case of Painleve 1, there are roots throughout the complex plane. For truncae, solutions are only in 3 of the 5 sectors, and in the tree truncae, they're just in 1 sector alone. So you're getting this tree truncae solution of Painleve 2, or Painleve 1, sorry. So let's move on to the second Painleve hierarchy. You can get a hierarchy of equations effectively by taking the modified quarter vector Friese equation hierarchy and just making a scaling reduction of it and taking 1 integration. And you get these equations of order 2, 4, 6, etc. And the rational solutions have a very similar form to what the rational solutions of Painleve 2 are. They're a logarithmic derivative of the ratio of 2 polynomials, which have the same degree, a half n plus 1, and you can express these as Wronskians. Specifically, you now define the Wronskian to be defined through this formula here, where this is an exponential. Now for capital N equal to 1, that's when I got Painleve 2. So it's just, this should be, so that should be a 2n plus 1 there, not a 3. And then you just take again, just as you did for Painleve 2, you take a Wronskian of the odd ones, and then this logarithmic derivative gives you the answer. So you might want to ask, what happens to the roots of this Qn superscript n as little n goes to infinity, or as capital N goes to infinity? Now we know that the largest root of this grows like little n to the 2 capital N over 2n minus 1, which agrees with the result for Painleve 2 when capital N equals 1. Now, if you keep little n fixed and increase n, so you take little n to be quite large, you take little n to be 5, so you first get pentagons, septagons, nonagons, etc. So they're just these regular structures with various patterns that you're getting in the middle. So this is just as I'm keeping little n fixed and changing capital N gradually. Now, if you do the other way around, which is what I've done here, I've taken capital N now to be 25. So these are actually going up in the polynomials themselves, expressed as polynomials with a variable of z to the 51, 25 to 225 plus 1. And so for n equals 40, you just simply get almost concentric circles of them. And then gradually, as the n becomes larger, you get more and more eccentric patterns, or more and more varied patterns as you go on. I should say that most of these also have a 0, z equals 0 is a root, but I've not plotted it. I took it out with a way of actually generating what these actual roots actually are. So this is what's happening as you're getting n, capital N going to can become large as well. Now, what I think is happening is that as you increase, they will all tend into a circle. And when I looked at the scaled ones, it appeared at one stage as though it's going to be the unit circle. Unfortunately, that theory went out of the window when I started getting numbers slightly above 1, but such is life. It could be, but the limit of what these actually are is actually what's not known. Okay, so now let me move on to Painleve 4. So now with Painleve 4, we have 2 arbitrary constants, alpha and beta. And so we have more choices. Now, it's now well known what the rational solutions are. They come in 2 sets. These were alluded to by Nalini last week. We have the set I put in blue, which are the blue dots on here, and the set in red, which are the red dots, which is the center of these triangles. Now, actually, on the lines that I've got here, you have solutions in terms of parabolic cylinder functions, and when they meet is when the parabolic cylinder function has a special case as a Hermite polynomial. And so that's when you get the rational solutions. And the plot is of A versus B, where A is alpha and B is the square root of minus 2 beta squared. Now, the way to actually describe these is in terms of a generalized Hermite polynomial. And this is the blue set. So this is the blue dots for these values of the parameters here. The only difference between these is I've got a 1 here and I've got a third there. And they come in three forms. And you'll see that the relevance of this later. You take this generalized Hermite polynomial, which is a Wronskian of n successive Hermite polynomials. And then you get these three sets of solutions which fill up everything I had before. Now, originally, Naomi and Yamada didn't write them as these these Wronskian representations, but they wrote them in terms of two recurrence relations, one for m and one for n, with various initial conditions. And you can generate them all like this, but it is a lot more work because you have to generate a whole line and then go in two different directions. You can actually also show that HMN satisfies this fourth order bilinear equation. It also satisfies some homogeneous difference equations as well. And it has a real zero unless n is positive. So only one of these sets of solutions have some bounded rational solutions. You need to have the first set with it's got to form n times 2n. And then you can actually have bounded and these decay as you go to infinite. You can also express them as a multiple integral, an n-fold multiple integral, which is a partition function in random matrix theory. And they also arise in connection with monic orthogonal polynomials on the real line for this semi-classical Hermite weight, where the recurrence coefficients of the three-term recurrence relation, which is important in one of the most important things in orthogonal polynomials, are explicitly expressed in terms of Hermite polynomials, but the ones that are bounded. Now, for the these generalized Hermite polynomials, if you plot the roots, they're in the form of squares or rectangles. So square if m equals n, and a rectangle otherwise. And so again, these are curved edges, and there's been some recent work on trying to understand what this region in which they actually are is. And particularly Zero, Ruffelson and Buckingham have studied the limiting regions for these zeros. And this is a figure taken from recent paper by Davide and Ruffelson, where they're looking at the zeros of H2216, and they've got this square root of 60 as the ratio. Now, I'm not going to say much more about the region, but again, if I was just playing with what I played with for the Jablonski-Vogel polynomials, and if you in the square case, but we know the roots grow like effectively root m if m is a multiple of n, for example. So if I take the square ones, so I've got 18, 22, 24, and you see the threefold symmetry coming here, and the fourfold with 16, 20, 24. And if you then do it in the rectangular variant, I've now put 4 of them together, and you keep the ratio the same. This is 4 to 3, and this is you just keep these ratios exactly the same, and you see the 5 to 4, and you see the 5 by 4 there, and you see the 4 by 3 there's in squares coming out of those then. And I've done the ratio here by putting the square root of n plus n, seems to be an appropriate one to do here. You can see they're all tending to a certain region. So. Now, if you look at Painleve 2, and you look for, in terms of the generalized Hermite polynomials, if m is r times n for some non-zero r, then we know that the alpha and the beta have this particular form that is going to look like an, a multiple of n, and beta is going to look like minus 2b squared, so it's a multiple of n squared for some constants and n, a and b. And again, if I do the same what I did for Painleve 2 and look for an equilibrium point, so I now know that it's going to grow like, w is going to grow like root n, and z go like root n as well. And so you have to see that eta and xi now satisfy this equation here. And then using the same kind of ideas I used for Painleve 2, you can show that if you make this transformation here, and what you get is effectively a rescaled version of Painleve 1, providing that n plus xi is non-zero, and then something that's of order n to the 2/5. So in a rescaling, you get that you need to have that eta and xi have to satisfy this quartic, but also to get this, you have to satisfy this cubic as well, which is actually the differential of 1. You just like I did for Painleve 2, you have to have it to be able to get this reduction. Now, it's well known there's been a reduction of Painleve in a limiting case for Painleve 4 to Painleve 2, but this is now Painleve 4 to Painleve 1. In some respects, that's not too surprising because discrete Painleve 1 arises from the Backlund transformations of Painleve 4, so you do expect a limited case there to happen. And if you actually look at the discriminant of this, the quartic, then you get an optic equation for xi. So, but it's in xi squared. So if you look at this polynomial, you can show that this only has 2 real zeros. So we know it tends to infinity as x goes to plus or minus infinity. At 0, it's negative, and the derivative, wherever it's a derivative, it's always, at those points, is always negative. So you can see that P only has 2 real zeros, and so therefore the discriminant has 4 roots, 2 which lie in the axes, and 2 complex roots which have a form. So that gives you where that rectangle, the points of the rectangle are going to be. Now, so now let's look at the other sets of solutions that you get. The first type of these were written down by Okamoto in 1986. And he wrote down them in terms of this differential difference equation and recurrence relation, just a similar way to how the original ones for Painleve 2 in terms of Jablonski-Vogel polynomials were written. And then the solution is minus 2/3 z plus the logarithmic derivative of 2 of these. And then this satisfies Painleve 4. And you can actually work these out. Again, it has the property that you don't get a rational function, you get a polynomial. The polynomial degree n times n plus 1, which is monic in zeta, which is square root of 2 times z within two coefficients. Okamoto wrote down a second set using a slightly different recurrence relation. And again, it's a minus 2/3 z times this logarithmic derivative. And now you get these are polynomials of degree n squared. These give you two, so these give you two sets of these equations. Now, if you actually look at them, look at the roots of them, it can be shown they have deep-dimensional forms. But R, it's starting with H2 tilde, which is just a scaled version of a Hermite polynomial. And you take take every third one starting with H2, and the S's every third one start with H1. And what you see is that the R polynomials, these now have two triangles. And the S polynomials have these two triangles, again with these curvilinear sides, but they now have a row of roots that lie on the real axis. So from then, it was able to generalize these to create what are now known as the generalized Okamoto polynomials. So if we define a QMN, so you remember that for Rn, they were every third one started with H2, and Sn every third one started with H1. So if you now combine that, and then what it turns out to be important is actually the difference between M and N in this QMN. And if M is bigger than N, then the logical thing to do is to have a sequence 1, 4, 7, etc. going to 3n plus 3n minus 2. And if n is bigger than m, then it's better to write them in this particular form, and they'll appear logical y in a minute. So why we get those. And then we can get all the solutions, what the red dots in the original figure I had, in terms of these three sets of solutions. Just like for the generalized Hermite, there are three sets of solutions and for three sets of parameters. So if we look at the properties of them, they were originally defined in terms of these recurrence relations. Again, one iterating m and the other iterating n. And you can also show they satisfy a fourth order bilinear equation. And this is the fourth order bilinear equation it satisfies. Effectively, they satisfy it, the logarithmic derivative of sigma mn satisfies a Painleve 4 sigma equation, from which you can derive this fourth order equation.
Peter, I have a question on this point.
Yeah.
So you have shown that the rational solution of Painleve equations, of the Painleve equation, can be written in terms of Wronskian, of some particular Wronskian of Hermite polynomials.
Yep.
So if I turn around the question and ask you, given an arbitrary Wronskian of Hermite polynomial, can I find a rational solution of some Painleve equation?
That is a conjecture due to Veselov of some equation in the hierarchy.
Yeah, some, but like
He doesn't know which one.
Yeah, exactly. So is there any way to guess or to?
Not that I know. I'm going to show you some more general solutions in terms of different combinations of them.
Okay.
But in principle, I mean, that was one of the a conjecture due to Veselov in about 2001. where he reckoned that you could do it. But I mean, yes, it is a good question of here you've created a specific Wronskian to get your solution, but you can just take any kind of Wronskian and then what happens, and then see can you engineer it backwards.
Yeah, it is related to the other conjecture by Felder, Emery, and Veselov about the zero root of Wronskian over Hermite polynomials.
Yes, I mean the zero root is, I mean z equals 0 is the only multiple root we've ever found.
So if you have a Painleve kind of equation, maybe you can prove it, but if you, just by the Painleve equation.
You could. I mean, there's a lot of structure to these, which is something that we're currently looking at in a different context. And certainly there's been various things looking at these Wronskian, just studies of Wronskians of Hermite polynomials purely for their own sake. So they not only arise in Painleve, they arise in these exceptional polynomials, and they arise in various aspects of mathematical physics as well, where you just get Wronskians of Hermite polynomials. And so it's a very interesting thing. And the Hermite is almost the simplest one. I mean, if you go back, you could do the same for the Painleve 2. It wasn't a Hermite, it was because Hermite has a quadratic in the generating form. For Painleve 2, the generating functions had cubic, and you can then ask lots of other questions as well. There's a sort of a semi-infinite number of problems you can ask for graduate students to look at.
Thank you.
And what patterns do they get, and how can you explain the patterns, and even understand the patterns? Anyway, so this, okay, does that answer your question?
Yeah, thank you very much.
Okay, so for the generalized Hermite polynomials, what we know is that in the ones I've called in sigma, these are where m is the original QMN, the m is bigger than n. These have a rectangle. They have a rectangle as a shape in the middle, and a triangles on the edges. And the difference between the size of the rectangle and the triangle is 1. Whereas the sigma ones, which arise when n is bigger than m in the original definition of QMN, the rectangles and triangles have the same values. Now, there's been some work very recently by Buchanan and Miller to look at what happens for large values. And that's still, I think, ongoing work. So that's in the square case. When they're not square, you're going to get rectangles and triangles appropriately lined up. And if you play the game I have already been playing of trying to make some kind of scaling of them and putting 3 together, then these go up 9, 12, 15, or 8, 12, 16. You see this sort of fractal kind of behavior kind of happen. I have no idea what it's just, but just doing the rescaling and put them together, you saw that. And equally, if you then do to slightly different ratios, then you get these ratios working like that as well. So it does seem to be something, there's a lot more internal structure of these roots that are going on that we didn't know about. Okay, now, so let me now slightly change to move on to Painleve 4, but in a different form, in the fact that Painleve 4 can be written as this symmetric system that was mentioned by Nalini. These 3 autonomous, simple-looking ODEs, very innocent looking. They're almost like a predator-prey between 3. We've got 3 variables, not 2. And you then, because if you add them, you then get these 2 constraints that have normalized that the sum goes to minus 2z and the sum of the parameters to minus 2. And then you can get the solutions. You eliminate F1 and F2, you get Painleve 4, and you get these 2 sets of solutions depending on whether you start with minus 2, 0, 0, or minus 2/3, minus 2/3, minus 2/3. These are the only 2 possible solutions of these where it's a multiple of z. is the only two simple rational solutions you can get. And you can get the generalized Hermite from the first one, the generalized Okamoto from the second one. Now, Nalini mentioned you've got some Maclaurin transformations. I'm not going to go through that, but I mean, that is what you can generate them from. And you can then you can explicitly write these solutions down just as I had before. I'm just going to flash that by. You can take this, look at the slides later, but that's what is actually done. So I wanted to move on to mention finally this. You can extend this to a hierarchy of now you take 2n plus 1 of them, and you have to have these constraints. And you can see there are all types of different initial simple solutions, and two special cases, because they all add up to 2z, minus 2z, you either one of them to be minus 2z and all the others to be 0, or you can have them all the same. And if we look at the first one in the hierarchy, the second one in the hierarchy, A41, so you've got this fifth order system with these two constraints. Then there are three sets of simple rational solutions. Numbers 1, 3, and 4 had been well known, but number 2, where you get 2 minus 2z and a 1 plus 2z, not been realized, I don't think, until quite recently. And you can get these with cyclic permutations. And so with the Galena-Fuller book, we looked at these two extremes in terms of what we call symmetric Hermite polynomials and symmetric Okamoto polynomials. A symmetric Hermite polynomial is when you take in two sequences of Hermite polynomials, so one starting at m of length n, and one starting at m plus r of length s. And the symmetric Okamoto, when you take in them, you take in four sequences, 1 plus 5j, 2 plus 5j, 3 plus 5j, 4 plus 5j. And remember that originally I had just one sequence in terms of threes for the Okamoto and one block for the generalized Hermite. And you get these now sort of, for the symmetric Hermite, you get these interacting roots, but there's no root that's multiple except 0. And you can see that some of them look like the superposition of two of the generalized Hermite, but they're not quite, but they look almost right. If you go into the symmetric Okamoto, you get some more exotic patterns. You see a similar kind of shapes, but multiple times. We don't know quite what the relationship between the various parameters and what the patterns you're going to get are. I can flash by, there's lots of different patterns you can get. You can play these to your heart's content. What I wanted to do was go on to look at recent work that I did with Derek Gomez-Aldate, Grandante, and Robert Milson. You've got these four seed solutions, and they come into the three different categories. The first two, they involve some what I call two block Hermite polynomials. I've got 4 parameters, and the starting points and the length of the sequences. The new ones that we wrote down, there are 3 sets. So these are in terms of, the first 2 are just like the generalized Okamoto, and the third one is going up in powers of adding 3 at a time. You're starting at some arbitrary points, and the length is arbitrary. So that's the 2 parameters. And of course, what you have to have is R is not one of these numbers. Otherwise, the Wronskian will be 0. And then the 5 Okamoto are the ones that previously we called the symmetric Okamoto polynomials. And I'll just look at the 3 Okamotos instead, the new ones. And they call into 3 categories when R is multiple of an integer, it's 1 plus 3m plus n, or 2 plus 3n plus n, depending on these are the values m and n here. And you can, again, you can just simply play and get all kinds of patterns. We don't know the structure of these at all yet as to why you get them for different, of what these actually involve. These are just some of the 3 different sets that we've actually found, that are just simply all different kinds of pictures are going on. But there's a lot of work to be done at trying to understand what on earth and how these relate to the parameters and what kind of structure you're actually going to get. If you go on to the A61, so the next one, you're getting, you've got a whole lot more of possible simple exact solution, simple rational solutions, which is a multiple of z. And you've then got 4 different types of polynomials, depending on whether you have the 3 blocks of standard Hermite, or those that where you add in 3, add in 5, or add in 7, and you just have to have the parameters according to how many different sets you've got, you can actually do. So you can actually move this along a lot further. And those are some 3 block Hermite polynomials. Again, it's just like having 3 sets of the generalized Hermite put together. And there's some 7 Nakamoto polynomials associated with A6. So to conclude, I put all the rational solutions of these A4 systems can be expressed in terms of Wronskian, in terms of suitable sequences of Painleve equation of Hermite polynomials. And I say suitable sequence, which is answering your, it's sort of just saying what you were thinking, David, of what can you then get your sequence of Hermite polynomials aligned to one of these positions as you move up the hierarchy. So if you know that sequence, you can probably work out exactly which one you actually had. Now you can actually generate some, they were the affine-Wahl group A2N1. If you look at the affine-Wahl group 2N plus 1, so the odd ones, then you can get these as Wronskian terms of suitable sequences of Laguerre polynomials. But that's something that's been, because if you take the first one, you get Painleve 5. So if you take A31, it's Painleve 5. It's a system of 4 equations. And these results are all based on Darboux dressing change. They're related to cyclic Mayer diagrams and the theory of Schroeder operators of trivial monodromy. And we can determine the number of real and complex roots through the explicit Wronskian representation. But trying to understand the ratio of the patterns you're actually getting on the roots to the parameters in the problem is a real challenge. Okay, thank you.
Thank you very much for this very interesting talk, full of a lot of intriguing ideas. We fostered the research for a quite good number of years. Does anybody have any question or remark?
May I ask a question? So I wanted to ask about this fractal patterns. So do I understand correctly that they are not specific for the zeros?
Sorry, I didn't catch what you said.
So you have shown some plots with rows of 2 polynomials with not coprime numbers, like 16 and 12.
Yeah.
They are shown in different colors. So is it correct that such pictures are just a consequence of the fact that we draw 2 almost periodic patterns, and this is just a consequence of the resonance between the periods?
It could be. It's just sort of one of the curiosities that you see a pattern, and mathematicians seem to like pattern recognition and trying to understand pattern recognition and trying to understand some kinds of structures of going on. Yes, I mean, there could be some very simple explanations to why that is true, but it's just a curiosity. That I was just purely trying to show that when I did appropriate scaling, that they did fit into a region.
So that's because I've just draw same picture for very simple numbers, which are just I over n and j over n for I and j from 1 to n, and it looks quite similar to such pictures.
Yeah.
That's not another question.
So I don't know. It's just one of the curiosities you find of just trying to understand what the structures are. It just happened to it could be absolutely nothing. It's just purely something that you spotted when I was trying to put some together to show that they were tending to a region.
So I would guess that when you do these higher order rational solutions, if you're able to do the asymptotic analysis, you will end up studying Boutroux curves of higher genus. And that this more intricate pattern is due to the fact that these Boutroux curves of higher genus, they can have many different inequivalent topology. And for every topology, you would have like a region, which some geometric, a geometric region where you have quasi-periodic roots. And then you will have a lot of these regions, and then maybe the projection of one region on the other. I mean, it will be all, it should be all due to some geometry in the Boutroux curves of higher genus. This is my guess.
That seems a reasonable thing to do, but it will take some proving.
Yeah, it would take ages. Yeah.
I mean, trying to understand even the work on the asymptotic regions for Painleve 2 and Painleve 4 is non-trivial.
Yeah, as we were mentioning in the discussion session, our papers are becoming too long and they are getting impossible to read. So I think we should be able, we should be allowed to write shorter papers.
Well, I'm just trying to understand them. It's taken me a time to read them to try and understand what you've actually done. I apologize for that. They are difficult to read, but it's the best we could do. Yes, I'm just hoping they can find a simpler kind of way of trying to explain what's happening to people, where you're getting certain things from. To explain to a graduate student what is actually happening, where the reasons are coming from.
But like speaking of my results and also of the results of Miller and Buckingham, which are based on two different approaches, but which end up doing the same things. It's just that we have like a curve of genus 1 depending on 2 parameters, and we have to fix 2 real conditions. And so this region of poles is when these two real conditions are satisfied. And we go to the boundary will be like singular curves where these conditions are satisfied. And for Hermite polynomials, there is just one topology, which is admitted. For Okamoto polynomials, there are 5 topologies. That's why you have five regions. And for more complicated rational solution, we'll have much more topologies.
Well, I think in the Okamoto case, the original 2 sets derived by Okamoto would be a simpler place to start because they're a much simpler. But the regions are much. I mean, they're just like 2 versions of what happened in the generalist. I mean, in the Jablonski-Volbach. I would have thought they might be a simpler case to be looking to start to try to understand some of that. Okay.
Any other questions or comments? So, if not, let us pick our speaker again. Thank you very much, Peter. And I think we can quit the recording.